Okay, so here's what we're going to do today. We're going to greatly expand our ability to do calculus without really adding anything that crazy. We're not going to add any new rules, any new derivative rules. We're just going to change the way that we apply them, expand it. So we can do stuff like this now. If we know that y equals sine x, we can find y prime. But we can't do this. If we have y equals the sine of 2x, we're stuck. Okay? Because that doesn't specifically match one of our rules. We have a rule for derivative of sine x, but not the sine of 2x, or the sine of 10x, or the sine of x squared, or something like that, right? We can do something like this if we have f of x equals the square root of x. We can rewrite that as a power, and we can do the power rule, right? But we can't do this. If we have f of x equals the square root of x squared plus 1, can't do that, right? So what we're going to add today is something called the chain rule. And the first thing I want to do is I want to just give you a little insight into one way that you can sort of conceptualize the chain rule. Let's start off with the idea of an analog clock. Okay, and I want to know for an analog clock, everyone knows what I mean by an analog clock, right?
No.
Not that. So if for an analog clock, I want you to tell me what some rates of change are. I want you to tell me what is the rate of change. If we're going to define, let me define a couple things here. Let's define, how do I usually do this? Yeah, there we go. So if we let S equal the angular position of the second hand, and M is the angular position of some minute hand, no, how about the minute hand? And H equals angular position of the hour hand. I want you to tell me a couple things. I want you to tell me what is ds dm. What does that even mean, first of all?
Rate of change.
Okay, rate of change, good. Is the rate of change of
The second in relation to the minute.
okay, rate of change of the angular position of the second hand with respect to the angular position of the minute hand. That's always how we would say a rate of change. It means a derivative, but it's the rate of change of the top quantity with respect to the bottom quantity. What's the answer? Picture a clock. What's it going to be? 60 is right. Okay, how'd you get that?
60 seconds.
Okay, so, okay, that's true. Maybe a different way to think about that is, in order for the minute hand to make one revolution around the face of the clock, how many revolutions does the second hand have to make? 60, right? Everybody agree? Okay.
Doesn't make 60 though.
What's that?
No, 60 circles. 60 times around for the second hand for the minute hand.
No.
60.
Right, because a minute hand's going to go, every time the minute hand moves 1 minute, that's 1/60th of a revolution. Takes the second hand's got to transit the clock 1 time, right? Okay, so then this is 60. What is that number is meaningful?
60.
That's this one.
Say it again.
It doesn't go around 60 times.
The second hand?
It just is 60 little ticks.
Right, okay, but in order for the minute hand to go all the way around the clock once, how many minutes is that? 60. Okay, does that make sense? Okay, so what does that number tell us? It tells us something interesting. I mean, 60 is important. Well, how would you, if you were gonna explain this to a person who was not in this advanced math class, a younger student, what would you say, okay, that 60 makes sense because, what?
60 seconds per minute.
60 seconds per minute. If we wanted to talk about like relative, this is, even for people that are in physics, this is way ahead of where we are now, but we're eventually gonna talk about something called angular velocity, or right? So angular velocity tells us the rate at which something that is rotating sweeps out angle. Okay? How are the angular velocities of the two hands compared?
The second hand is 60.
Second hand is 60 times faster. Yeah. The second hand moves around a clock 60 times faster than the minute hand does. Right? Everybody agree with that? Okay, good. Good. Okay, so we got that. So ds/dm is 60. Now I want to know what is dm dh. Okay, what does that even mean? So how would somebody state for me very precisely, correctly, state how we would describe that derivative as a rate of change?
Rate of change of minutes relative.
Okay, and really we have to maybe the rate of change of the angular position of the minute hand with respect to
The angular position of the hour.
the angular position of the hour hand. Okay? What's this answer? 12. Exactly, it's 12. Right? Because the minute hand has to go around the clock 12 times for the hour hand to go around the clock once. Agreed? Okay. Okay, so now here's where the chain rule comes into play. Can you tell me what is ds dh? So that's the rate of change of the angular position of the second hand relative to the hour hand. 720 is right. How'd we get that? Yeah, because we're multiplying the two rates. Okay, this is one way. This is not, frankly, the way that we're going to use the chain rule most of the time, but it is a way to think about it. If I want you to notice a couple things about this. If we write down ds dm times dm dh, what do you notice algebraically? What do you notice about the product of those fractions?
Some cross cancel.
Yeah, we can cross cancel, can't we? Cross cancel the dm's, and that works. That works in calculus because we're taking the rate of change of the second hand with respect to the angular position of the minute hand, and then the minute hand with respect to the hour hand. This works as a product. Okay, and so we just end up with 60 times 12 equals 720. So what's that tell you about the relative speeds of the second hand compared to the hour hand?
700.
That second hand has an angular speed 720 times greater than the hour hand, right? Okay, so we'll come back to this example in the future, but that's your first glimpse of what the chain rule does. Okay, now it's going to seemingly do something much different here for you, but it's eventually will relate these two concepts. So how are we going to use the chain rule then to deal with something like that? The derivative of the sine of 2x. How in the world are we going to do that? This is kind of weird. I'm just going to try something. I've never done this before. This seems like this might be helpful to think about it this way. So if we want to do this problem, I'm going to write this like this way. Okay, so y equals sine of 2x. And I want to calculate, I want to get dy dx out of this thing. Can anybody think of a way that we could apply that thinking we just did? Okay, okay, so, yeah, we got something here. One thing we could say is, we could say this is equal to the derivative of, what am I gonna call this? The derivative of y with respect to, well, I'm gonna call it, yeah, this will be better. We'll do the derivative of sine of 2x with respect to x. Okay, what is the derivative of sine 2x with respect to 2x? Think about what's the derivative of sine hand with respect to hand? What's the derivative of sine theta with respect to theta? The derivative of sine theta with respect to theta is what? No, cosine theta, right? Right? We could write that rule down. That's one of our standard rules. We wrote it in terms of x. I want to make a point here. The derivative with respect to x of sine x, we wrote, is cosine x. That's no different than saying the derivative with respect to x of sine theta equals cosine theta, right? It doesn't make any difference what the variable of differentiation is. I could call it an x or a theta or an apple. It makes no difference. I'm going to get the same result. The pattern is the derivative of sine of something equals cosine of that thing, right? So the first part of this then is going to give us back cosine of 2x, but we're not done. We need to multiply that. If I want to get dy dx, right, and y, I'm taking the derivative of sine 2x with respect to x, aren't I? Right? I first differentiated with respect to 2x. Now what do I need to end up with? Let me rewrite this real quick here so we're consistent. So we're taking the derivative of sine 2x with respect to x, right? We're differentiating sine 2x. So there's the first link in the chain. What do I have to multiply that by, though, if I want my result to be this?
Derivative of 2x over derivative of x.
Okay, I got to do the derivative of 2x over the derivative of x, right?
Can you explain why?
Say that again.
Why?
Why is that? Because of this. How did we get, if I want to calculate ds dh, and I know ds dm and dm dh, if I multiply the product of ds dm times dm dh, then I get the result. Because I'm taking the derivative of s with respect to here in the first factor, right, the first rate, is what I'm using to gauge. It's like an intermediary or middleman. Derivative of s with respect to this middleman times the derivative of this middleman with respect to h is going to bridge the gap between the s and the h. Okay, we knew that it took, this rate was 60. The second hand moved 60 times as fast angularly as the minute hand did. The minute hand moved 12 times as fast as the hour hand. And so the product of those two tells us how fast the second hand moves with respect to the hour hand. Yes, Nick?
So there's 60 seconds per minute. I'm thinking about revolutions.
Right.
And there's 12 minutes per hour?
No.
I don't understand.
No.
It's broken up into 5-minute increments, but why is that?
Why is this one 12
Yeah,
instead of,
60.
because how many times does the minute hand transit around the clock for the hour hand to go around once? 60. I mean, no, 12, right? Right?
Yeah.
Think about here's the minute hand, right? Here's the hour hand. For the hour hand to go from noon to 1 p.m., that's one rotation of the minute hand, right?
And then, so multiply
2,
that by 12.
3, 4. Right? Does that make sense? Right? Okay. Does that make sense? Yeah.
That's what we have to do. French said 12 to 1, but they're not.
So to go from 12 to 1, the minute hand is going to get 60 minutes. So the minute hand is going to go around once. It's going to go around the dial once, right? The minute hand has to go around the dial 12 times for the hour hand to go around once. See what I'm saying?
No.
So on the next problem, are we just gonna take the derivative of 2x?
Yeah, we will. But let's go back. Okay, I want to make sure everybody gets this part. And it's not like this is crucial. I mean, this isn't like a crucial thing to understand calculus, but let's just make sure we understand this. So when we're calculating ds dm, right, we want to know how fast, what's the rate of change of the angular change, right? How fast is the second hand rotating compared to the minute hand, right? For the minute hand to go around the dial, everybody agrees that's 60 minutes, right?
Yes.
Each minute requires the second hand to go around once. So everybody agrees with that one. The minute hand, but the second hand moves 60 times faster than the minute hand. Okay, now,
And wait, but that's not because there's 60 seconds in a minute. That's because there are 60 minutes an hour. If you think about it, because one rotation is the hour.
you're right.
Okay,
You're right.
That's how you. So you have to think about it as if you're going to the next highest.
Well, kind of. I mean, we're just thinking about, all you have to do, you're right. That's one way of conceptualizing it. But you're just thinking, if I'm looking at a clock, how long does it take, if I want to watch that minute hand go all the way around the dial, if I have that much time, how many times is the second hand going to go around? 60, right? Does that make sense? One way to think about that is, every time the second hand goes around the dial, the minute hand is only advanced 1/60th of the way around, right? Okay, and it's an hour, you're right. Now move up to the next relationship, hours compared to minutes,
But you're
right?
today's.
So in order for the hour hand to advance 1/12th of the way around, just 1 hour, right? How many times does the minute hand have to go around? Once, right? See what I'm saying? The minute hand is going to go around, it's going to go through 60 minutes, which is 1 revolution, every time the hour hand advances 1/12, right? It might be helpful to think, how long does it actually take for the hour hand to go all the way around once? It's half a day, 12 hours, right? Does that make sense? So for the hour hand to go around, 1 time around, which is 12 hours, the minute hand has to go around 12 times, right? Does that make sense? Okay. So then on this one over here, if we just compare, now we're going to do this a much better way, by the way. This is just kind of a hokey way of getting us thinking in the right way, but we're going to come up with a much better technique for using the chain rule to do derivatives. But what we'd have to do is we got the product of these two derivatives here, because these two rates, because that's the middleman that's going to cancel, right? If we know how fast, what's the rate at which the function sine 2x is changing with respect to 2x, and we know how fast 2x is changing with respect to x, then the product of those two would tell us how fast is the function sine 2x changing with respect to x, right? So this answer is just cosine 2x, right? Because, once again, the derivative with respect to hand of sine hand is cosine hand. Doesn't matter what's behind my hand. If it's the same thing here as it is here, the answer is cosine of that, right? We could call it theta if we want to. It's fine. Derivative of sine theta equals cosine theta, right? Oh, sorry, with respect to, there is a mistake here. What's the mistake? On this bottom with respect to, should be with respect to theta, right? The derivative with respect to theta of sine theta is cosine theta, right? So here we've got the derivative with respect to theta of sine theta is cosine theta, right? Okay, that's our pattern. What's the derivative of 2x with respect to x? 2. So my answer is 2 cosine 2x.
What canceled?
This denominator is the same as that numerator, right?
Uh-huh.
And so that's just telling us how the chain rule works. The chain rule, it works algebraically, even though it means something completely different. It's consistent with algebra, right? So what are some ways we could make this maybe a little bit easier? Well, there's a couple ways we could do this. We could, for example, 2x is kind of inconvenient, right? Question?
I thought the derivative of 2x canceled
Yeah,
out.
that's my question.
So
Why,
does that mean
what cancels?
we still have to?
Well, okay, but it's not, it's only, okay, it's not really canceling. It didn't cancel there, did it? Right, it didn't cancel. It's just that algebraically, we could see that ds dh is equivalent to the product of ds dm times dm dh. Algebraically, right, we can see that algebraically, I just get ds dh there, right?
Yes.
But the way I'm going to find it is by multiplying, that's a number that I know.
So-
ds dm is 60, dm dh is 12, right? I don't know this one directly.
So
You guys would have had a hard time telling me.
the only reason that you're canceling is to prove that those two multiply to get that. That's the only reason.
Right,
you're
right.
canceling.
So here's another way to think about
I
it.
find that you don't cancel anything.
You're breaking it into different, into more than one product. If I had just asked you directly, how many times does the second hand go around when the hour hand goes around once? You all would have struggled a little bit to tell me, because you have to think about multiple things to make that happen. But it's relatively easy to tell me that this is 60 and that's 12, right?
Yes.
And so therefore, we can write this in a way where I can take the product of those two rates to find this one compound rate, right? You get the idea? Okay, so then, same thing here, right? We know that, we don't know this directly, but we know this. That's just a rule, right? This is just telling us the derivative of sine theta with respect to theta is cosine theta. Well, my theta is a 2x, okay? And then the derivative of 2x with respect to x is 2. So I know each of these small derivatives. Therefore, this big compound derivative is just a product of those two rates. How could we make this a little bit easier? Well, if we took that same problem, and bear with me here, because I think this is I've never done it exactly this way, but this seems like this is going to be good. If we want to do the derivative with respect to x of sine 2x, well, one thing we could do is let's make what's called a u substitution for derivatives. Let's say, 2x is kind of clumsy. Let's just instead define u as being 2x. Okay? Then what does this become? Then this comes the derivative with respect to x of sine u. Right? So what can we do with this then? Well, if we want to know we're trying to find out what the derivative of sine u is with respect to x, we could write that as the derivative with respect to u of sine u times what? What do I have to get? If I want to get, I'm trying to find.
du over dx.
Yeah. Do you see that? Right? Right? If I'm trying to get, let me write this as a ratio. This is just the derivative of sine u with respect to x. I could do the derivative of sine u with respect to u times the derivative of u with respect to x. Right? And then algebraically, we can see that those are equivalent statements, but this is a rate that we know, that's a derivative that we know, and that's a derivative that we know. Right? You get the idea? So if u equals 2x, what is du dx? What's the derivative of 2x with respect to x? 2, right? And what's the derivative of sine u with respect to u? Cosine u, right? So we get cosine u times 2, which is 2 cosine u. But then we could say, okay, well, let's reverse the substitution. what is u really? It's 2x. So my answer is 2 cosine 2x, right? Okay, get the idea? Okay, there is a better way. This works, but we're going to come up with a better technique for this. So let's think of it this way instead. Let's think of this as being, let's write this instead of the derivative in ratio form, let's write it in function form. So if we want to do something like this, if we want to do the derivative with respect to x of f of g of x, what's this equal to? Okay, this is just equal to f prime of g of x times g prime of x, right? Hey, I'm right in the middle of something. What's up? Yeah, that's just, they got it wrong then. I'll explain later. They'll just say that if it's wrong. Okay, bye. Okay, so then let's apply this to what we just did. If I'm taking the derivative with respect to x of, what do I have, sine of 2x, what's this saying? It's saying that I'm going to take the derivative of the outside function, which is sine, with respect to whatever's inside, right, times the derivative of what's inside. So you can think about this. Derivatives are like onions or ogres. They have layers. And so we have to differentiate from the outside in. We're going to peel the layers one at a time. So at the outer level, we're going to look at this and say, okay, the outside function is sine. What's the derivative of sine hand? Cosine hand, right? So we end up with, first layer is going to be cosine of hand. Don't even care what's in there yet, right? Okay, now we'll look in there and say, all right, well, what's inside? Well, it's a 2x. So now if we peel away that outside layer, we go to the next layer. What's the derivative of 2x? 2. There's our answer, 2 cosine 2x.
Okay,
So-
that I
Right? They're the same thing. They're exactly the same thing. It's just a different way of looking at it. This is sort of the culmination of the thinking that we did before, right? So we can do a harder one. Let's try something like this. What if we have I'll do this. Okay, how about that one? Okay, we want y prime, right? So first of all, we have to write this in a way where we can see all the layers. So we probably want to rewrite that square root so it's useful. The way that we understand how to differentiate. What's that going to be? Well, 1/2 power, right? We got to make it a power rule thing, right? So we could write this as the quantity x squared plus 1 to the 1/2, right? And if I want to find y prime, I'm going to have to differentiate this layer by layer. There are 2 layers, so I must need 2 links in my derivative chain. I have the product of 2 derivatives, or 2 rates of change. So outermost layer, if we just blur our calculus vision here, what's the outermost layer of this? Okay, it's 1/2 power. And we don't care what's inside. We're not going to look inside yet. That outermost layer, if I have hand to the 1/2, what's the derivative of hand to the 1/2? 1/2 hand to the negative 1/2. There you go. So we get, first layer is, we're going to get 1/2 hand to the negative 1/2, right? Times the derivative of hand. Well, so I guess we can fill this in now. Now we peel that outer layer. What do we have inside? We have an x squared plus 1. So what's the derivative of the inside then?
2x.
Okay, so our answer is, if we just put that in the right order, we would just end up with the 2 and the 1/2 cancel. I just end up with x over the square root of x squared plus 1, right?
Oh,
Oh, never mind.
Because it's a negative 1/2, so it goes to the bottom, right? Get the idea? Right? So it's just layers. We got to go layer by layer from the outside in. Where the, well, 2 times 1/2. Right, so these just cancel. Okay? All right, so all right, let's try a really hard one. How about?
What about like multiple layers?
Yeah, exactly. So let's try something. Let's try something like this. Okay, how about this? Wow, lots of layers. So there are lots of layers there, right? We probably want to rewrite this one time. Tangent squared is a shortcut for what?
Sine over cosine.
Well, okay, but if I say tangent squared of theta, what is that really?
Tangent theta.
Tangent theta quantity squared, right? Everybody agree? Okay, so then so let's rewrite this as sine, and we'll use script brackets. We're gonna have lots of layers here so we can keep them straight. We're gonna have sine of, next layer is the squared, right? And what's inside the squared? Well, that's gonna be a tangent of square root, and what's the square root? Huh, no, you got more layers. Yikes. Tangent of x squared minus 1 to the 1/2. How many layers we got there? 1, 2, 3, 4, 5 layers. So how many products are we going to need? How many links in the chain? 5. We're going to have to do 5, differentiate 5 layers to get this, right? So the first thing is, but I want to show you that, this is like the hardest possible chain rule problem, and it's not that bad. Just follow the rules. So what's the first layer?
Sine.
Sine of hand. What's the derivative of sine hand?
Cosine.
Cosine hand. So the first layer is cosine of all that stuff, right? Of all that stuff in there. I guess I better write it. There's gonna be a lot of writing. Cosine of tangent right? Okay, times, what's the next layer? So it might be good to, I know what we can do. Oh, this would be great. This is such a big one. To keep track of everything. Oh, this is great. This is great. I like this. Let me scoot this whole thing down a little bit. And let me grab, if I can just possibly grab just that gap. Well, okay, now if I erase, oh, this is good. This is good. Oh, all right. There we go. Okay, so let's just erase the layers one at a time as we go through them. Okay, so we took care of the first layer, and that's the link that we got. So let's erase that one. Right? Next layer. Squared. Derivative of hand squared is 2 hand. Okay, so now we've got 2 times hand, which is tangent of x squared minus 1 to the 1/2. Right? And so now we can erase squared. Okay, good. Times, what's the next layer? Okay, derivative of tangent hand is secant squared hand. Okay, so the next one's going to be secant squared of hand, which is x squared minus 1 to the 1/2. We can erase that layer.
What's that one? Which layer was that?
That was the squared layer. Oh, no, the tangent layer. Tangent layer. Okay, what's the next layer? 1/2. Okay, so now I'm going to have to go down to the next line, but now we've got times derivative of hand to the 1/2 is 1/2 hand to the negative 1/2, and the hand is just an x squared minus 1, so we can erase this layer. And finally, we're at the middle. What's the derivative of x squared minus 1? 2x. 1, 2, 3, 4, 5 links, right? And now all we'd have to do is just put that in the right order, but that's our answer. That's the calculus, right?
How big would that be?
What's that?
That'd be really big, right?
Yeah, but I mean, it's not horrible. We could just, we can do some cancellation. So the 2 cancels with the 1/2. So what would I get? I would put the 2 out front. I'd get 2 times the cosine of all that garbage times the tangent of that stuff times the secant of that stuff, and I'd have an x out front too,
So-
right? 2x, and then I just would divide that by the square root of x squared minus 1, and that'd be it. So it's a big answer.
That's it.
But-
Not that bad.
I mean, that's it though. That's the derivative function.
How many layers is it gonna have on this assignment?
Oh, I don't know. Not that many. But the point is, you could do that, right? I mean, it's not like the process is that daunting, when you think of it that way, at least. Okay. We'll call it a day.